Hello future engineers, welcome to my YouTube channel. If you're still new to my channel and you like what I'm doing, please don't forget to share my videos to your friends and to your friends' friends. That's one way you can keep me going, inspired and refreshed. Now if you find my videos interesting and important to your studies, also please don't forget to subscribe. So this is a portion of distributed forces. So still on locating centroids of volumes, areas, arcs or lines, and the corresponding derivation of formulas for volumes as well as for the locations of the centroids or center of gravity, which is very important in the succeeding topic on uh, beams subjected to loadings, line loads, concentrated loads, or surface loads. Level 31. Use integration to find the centroidal coordinates for the volume obtained by revolving the area shown about the x-axis. So here is a given shaded region and we have a parabola here with vertex here, and it is to be revolved about this x-axis here. So if you consider a strip, vertical strip, then the y of this curve is the y of this parabola. The lower y is the x-axis, so y is 0, therefore the height of this strip is just y, and the thickness is dx. So the variable of integration is x. Then if we revolve this about the x-axis, it generates a disk, which is area of circle times thickness. That's the differential volume of the element. The centroid lies here, so that every point on this circular disk is equidistant from the y-axis. So that means the x-coordinate is just the centroidal x-coordinate of the element, differential element is just x, or x sub c is just x. So the volume is pi radius y square thickness dx. That's the volume of that disk, pi y square dx. So therefore volume is integral of pi y square dx. So the differential volume is pi y square dx. Substitute the value of y. So integral from 0 to b of pi h quantity 1 minus x square over b square square dx. Expanding, so volume equals pi h square times the integral 0 to b of 1 minus 2x square over b square plus x to the fourth over b to the fourth dx. So integrating, volume equals pi h square quantity x minus 2x cubed over 3b square plus x to the 5 over 5b to the fourth from 0 to b. So substituting, volume equals pi h square quantity b minus 2b cubed over 3b square plus b to the fifth over 5b to the fourth, then lower limit 0 because everything has x, and the lower limit is 0, so everything will be 0 here. So these are like terms in terms of b, so 1 minus 2/3 plus 1/5 times pi h square. So the volume can now be computed 8 over 15 pi b square. Now, if you're familiar with the location of the centroid of this parabola from the x-axis, then we can use Pappus-Guldino's theorem, which is volume is just area of parabola times 2 times distance traveled by the centroid. So that is if you can remember that. So assuming you remember, the location of the centroid of parabola from the x-axis is 2/5 of h, because this from the vertex to the centroid along the axis of the parabola is 3/5 of h, so this is 2/5 of h. So if this centroid is, if the entire region is revolved about the x-axis, this will generate a circle. That's the distance traveled by the centroid, and the circumference of that circle would be 2 pi because we have one revolution times this radius of revolution, 2 pi times 2h over 5. So volume is also area of parabola, which is 2/3 base times height times distance traveled by the centroid, 2 pi times radius of revolution 2h, 2 pi radius of revolution 2 fifths of h. So the volume to check is also 8 over 15 pi p h square. Then for the centroidal location, volume times xg equals integral of x sub c dv, where xg is the x coordinate of the solid, entire solid when revolved about the x-axis. X sub c is the x coordinate of this differential element, which is just x. So substitute volume 8 over 15 pi b h square x sub g equals integral equals pi h square. Let's just copy this and involve x this time because this is dv. So pi h square quantity 1 minus 2x or b square x to the fourth over b to the fourth dx. Then x sub c is just x here. Then cancel pi h squared, then we have 8 over 15 b xg equals integral from 0 to b of quantity x minus 2x cubed over b squared plus x to the fifth over b to the fourth dx. Integrating, so xg equals 15 over 8b quantity x squared over 2 minus x to the fourth over 2b squared plus x to the 6 over 6b to the fourth from 0 to b. So this is 2 because this is supposed to be 2x to the fourth over 4b squared, so simplifying, that's the result. So xg is 15 over 8b quantity b squared over 2 minus b to the fourth over 2b squared plus b to the 6 over 6b to the fourth, then minus lower limit 0. So these are like terms, b to the fourth, and using your calculator there, because this will be cancelled, so we have b squared over 6 as net value, b squared over 6, so 15 over 48, or simplifying, it is 5 over 16, 15 over 48 or 5 over 16b. Then by symmetry, yg and z sub g 0. So that's it for this problem. Level 32, use integration to find the centroidal coordinates for the volume obtained by revolving the area shown about the y-axis. So this is the figure. If we revolve this about the y-axis, it will generate a paraboloid evolution, and you know that the volume of paraboloid evolution is 1/2 the volume of the circumscribing cylinder. In this case, b will be the radius, so we expect that the volume would be pi b square h over 2. And the centroid, because this is paraboloid, is 1/3 of h from the base, 2/3 of h from the vertex. So let's have the solution and prove or show that those are the mentioned answers. So I'll consider vertical strip again, and if we revolve this about the y-axis, it generates a cylindrical shell. So this is y. Upper y is the y of the parabola, lower y, the x-axis is y0, so the height is just y. So that's thickness dx, the variable of integration again is x. So this is the differential element, which is a cylindrical shell, and supposedly I will not discuss this anymore because you have experience with this in integral calculus. The centroid is here of the element, so therefore y sub c is just y over 2. So that's y sub c, which is y over 2. The volume of the cylindrical shell is, if you cut this and flatten out, it is a rectangular plate with length of the base, circumference of the base, which is 2 pi x, because every element of this vertical strip is at distance, equal distance from the y-axis, and that is just x. So again, imagine that this cylindrical shell is a rectangular plate discussed in integral calculus. I hope you can remember. The base is 2 pi x, the height is y, and the thickness is dx. Therefore, the differential volume is volume of the rectangular plate, 2 pi x, height y, thickness dx. So v is integral of dv, and dv is 2 pi x y dx. Substitute the value of y. So volume equals 2 pi integral of x. Y is h quantity 1 minus x squared over b squared dx. So volume equals 2 pi h, then integral of x minus x cubed over b squared dx. Integrating 2 pi h quantity x squared over 2 minus x to the fourth over 4b squared from 0 to b. So that would be 2 pi h quantity b squared over 2 minus b to the fourth over 4b squared minus lower limit 0. So 1/2 minus 1/4 is 1/4. 2 pi h divided times b squared over 4 is pi b squared h over 2, as expected. So that's the volume. Then volume times yg. By the way, if we apply Papos-Guldino's theorems, then the volume is equal to area of parabola times distance traveled by this centroid, which is circular, and that would be 2 pi times this radius of revolution. And can you remember this distance? If not, you cannot check the volume. But this is 3/5 of b, 3/8 of b, because this is 5/8 of b. This is the axis of the parabola, so that's 3/8 of b. So by Papos-Guldino's theorem, then we have volume equals area of parabola 2/3 base times height times 2 pi radius of revolution 3b over 3/8 over b. And if you check that, that's also pi b square h over 2. So it checks. Then volume yg equals integral of y sub c dv. Y sub c is just y over 2. So pi b square h over 2 yg equals integral of y over 2, then 2 pi xy dx. Let's go back to this first. So cancel 2, cancel pi. So we have b square h over 2 yg equals integral of x y square dx. Substitute the value of y. So yg equals 2 over b square h, integral 0 to b of x, then quantity h, 1 minus x square over b square square dx. Expanding, so we have yg equals 2h over b square after we cancel h in the denominator. Then we have x 1 minus 2x square over b square plus x to the fourth over b to the fourth dx. Yg equals 2h over b square, quantity integral of x minus 2x cubed over b square plus x to the 5 over b to the fourth, then dx. Integrating, yg equals 2h over b square, quantity x square over 2 minus 2x to the fourth over 4, so minus x to the fourth over 2b square plus x to the 6 over 6b to the fourth from 0 to b. So substituting, yg equals 2h over b square, quantity b square over 2 minus b to the fourth over 2b square, so we can just cancel that. Then b to the 6 over 6b to the fourth. So we have 1/6 times 2h over b square, that would be h over 3 as expected. So then by symmetry, xg equals g sub g 0, because this is the axis of revolution. The centroid will lie there, so x sub g and g sub z 0. So that's it for this problem. Level 33, compute the coordinates of the mass center of the portion of the solid homogeneous cylinder shown in the figure. So this is the cylinder, and we have 3/4 of a circle. So let's have barred x, and let's have xg and yg. G sub z is, of course, because the area is constant from the base to the top, so it is just one half of 10 inches. So G sub g is 5 inches. But let's focus first on xg and yg. So let's draw the top view. So we can analyze. The centroid will lie there, and the distance in general is 2r sine theta over 3 theta, where theta is 135 degrees, or converted to radians 3/4 pi. So that's 135 degrees. This is also 135 degrees. 270 minus 270 divided by 2. So again, this distance is in general 2r sine theta over 3 theta. Then this is the y, this is yg, and this is xg, and both are negative and equal because they lie here. So yg is negative, xg opposite to the positive x-axis is also negative. So from the figure, let's evaluate 2r sine theta over 3 theta. 2 times 6 sine of 135 degrees over 3 times pi, 3/4 pi. 135 degrees is 3/4 pi radians. So simplifying, that's 8 square root of 2 over 3 pi inches. Therefore, xg and yg can now be evaluated. It is equal to this distance, this hypotenuse, times sine or cosine of 45, negative. So xg equals yg equals negative of quantity 8 square root of 2 over 3 pi sine of 45 degrees. So simplifying, we can now find xg and yg, negative 8 over 3 pi inch, and g sub z is, as mentioned earlier, 5 inches. So that's it for this problem. Level 34, locate the centroid of the shaded area between the ellipse and the circle. So here is the given figure. It is just area of ellipse minus area of circle. The area of ellipse is, because this is just half pi AB over 2 for the ellipse, then for the circle, pi radius square, so over 2, so pi b square over 2. So area equals pi AB over 2 minus pi over 2b square for the circle, semicircle. Factor out pi b over 2, then we have pi b over 2 times a minus b. So that's the area. Then area times xg, pi b over 2, a minus b, xg equals area of ellipse times 4/3 a over 3 pi. That's the x coordinate of the centroid of the ellipse. Then minus pi b square over 2, area of circle. Then 4r over 3 pi, where r is the radius of the circle, which is b. Then cancel pi b over 2. We have a minus b, xg equals a times 4a over 3 pi minus b times 4b over 3 pi. So factor out 4 over 3 pi. xg is 4 over 3 pi, quantity a square minus b square. Then let's factor a square minus b square into a minus b times a plus b. So a minus b xg equals 4 over 3 pi, quantity a minus b times a plus b. Then finally we can cancel a minus b, then have xg equal to 4 over 3 pi times a plus b. So that is for xg. Since by symmetry about the x-axis, the centroid lies somewhere here, and it lies on the x-axis, therefore yg is 0. Level 35, calculate the distance hg measured from the base to the centroid of the volume of the frustum of the right circular cone. Solved in two ways. So here is the given figure. First, let's solve this by integration. Let's have a strip, horizontal strip, so that the differential element will be a circular disc as shown, of radius x, thickness dy, and y is measured from the vertex from the top and going down is positive. So that is y. Then because this is h over 2, the overall height of this imaginary cone is h. So the radius here would be r over 2, half of r. So for the first method, volume is integral of differential volume. The differential volume is pi x squared dy. So integral of dv, volume from h over 2 to h, the limit h over 2 to h. This is our reference from the top. So pi x squared dy, where from the figure x as to y equals r as to h. So x as to y by similar triangles equals r as to h. So x is r over h times y. Substitute here, volume equals pi from h over 2 to h, integral of x squared, so r h y quantity square dy. So volume equals pi r squared over h squared, integral of y squared is y cubed over 3 from h over 2 to h. So volume equals pi r squared over 3h squared, quantity h cubed minus h over 2 cubed. Of course, lower limit is not shown, 0. So this is 1. This is h cubed minus h cubed over 8. So 7 over 8 h cubed, cancel h squared. So volume 8 times 3 is 24. So 7 pi r squared h over 24. So that's the volume, 7 pi r squared h over 24. Then volume yv first, because the location of the centroid is to be base from the base also. So let's solve for yv first, y from the vertex, which is, in this case, y sub c is just y also. So volume hv equals integral of h sub c dv, where h sub c is just y, because y is y sub c. So the distance from here to the centroid is at the center of this disc. So any point on the disc is equidistant from the vertex. So that's why y is just h sub c, also the distance of the centroid of this differential element from the vertex. But hg, not hv, we solve for this first. So hg from the bottom, from the base, is h minus whatever is the result here for hv. So substitute 7 pi r squared h over 24 hv equals integral of y from h over 2 to h of, this is dv. If we simplify pi r squared over h squared y squared. So pi r squared over h squared y squared, then dy. So cancel out pi r squared. So we have 7h over 24 hv equals 1 over h squared. Then integral of y cubed is y to the 4th over 4 from h over 2 to h. Simplifying, 7h over 24 hv equals 1 over 4h squared, quantity h to the 4th minus h over 2 to the 4th, lower limit 0 to the 4th, or 0. So this is 1 h to the 4th minus h to the 4th over 16. So 15 over 16 h to the 4th, cancel h squared, then times 24 over 7h. So 7h over 24 equals 15 over 64, 15h squared over 64. So cancel h, cross multiply, then hv is equal to 45 over 56h. Therefore, hg from the bottom is h minus 45 over 56h. So h sub g from the base is 11 over 56h. So that's for the first way. For the second way, let's have composite volumes because we already know the volume of cone and the location of the centroid, which is one-fourth of the height from the base. Remember that. So volume is volume of big cone, pi over 3 r square h minus volume of small cone, pi over 3 r over 2 square times height h over 2 also. So if we simplify this, the volume of small cone is pi r square h over 24 because this is 3 times 4, 12 times 2. So 1/3 minus 1 over 24. Again, the volume of the small cone, this cone here, is pi r square h over 24. So 1/3 minus 1 over 24 is 7 over 24 pi r square h. So which checks the volume here. Then apply Varignon's theorem. Volume times hg. So that's the location of the centroid. Then this is hg. So volume 7 over 24 pi r square h. hg equals volume of big cone pi over 3 r square h. Then the centroid of the big cone from the base is h over 4. So pi r square h over 3 times h over 4 minus volume of small cone. This is pi r square h over 24, and the distance of its centroid from the base is h over 2 plus again 1/4 of the height, 1/4 of h over 2. So this is h over 2 to the center of the upper circle or base. Then plus, because this is 1/4 of the height and the height is h over 4, so plus 1/4 of h over 2. So minus pi r square h over 24 times quantity h over 2 plus 1/4 of h over 2. So I hope that you can visualize. That's the distance of the centroid of this upper imaginary cone from the bottom, from the base. So simplifying, cancel out pi r square h. So 7 over 24 hg equals h over 12. And this is 5/8 times 1 over 24. That's 5 over 192h. So 1 over 12 minus 5 over 192 times 24 divided by 7. You will get 11 over 56 h. So that's it for this problem, and I hope that you were able to follow, especially the second part.